Hi, here is another interesting video under triple integrals in Cartesian coordinates. Um, this is actually very interesting. Um, so what we do is, I don't think there's anything that I need to change here. Work it out the way it is. Okay, so let's go ahead and work it out. So we have this one from 0 to 45, which is pi over 4. Then at this point we have 0 to natural log of sec z. Okay, just trying to change the color there. Okay, sec z. So when you integrate e to the x, you're still going to get e to the x. So that should be like e to the x evaluating from minus infinity to 2y. That is dy dz dz like that. Okay, so I still have this. That's from 0 to pi over 4. Then maybe to save time, let me just copy this and just bring it here. Okay, even better, time saving. So here you can go ahead and do the substitution. The upper limit is simply e to the uh, that is e to the 2y, because where there's x you're going to plug in with 2y. So if you plug in with minus infinity, you're going to get a 0. How does the 0 come about? Let me show you. So since you have like e to the power x like that, so if you plug in minus infinity, this will be like e to the minus infinity. So you don't want to deal with a value with like a negative power. So this will be like 1 over the same value to the positive power of that. That's like e to the power infinity. So the denominator is extremely large, like it's very large. Hence this just goes to what? It goes to 0. So that's why we said it goes to 0. We are thinking in those angles. Okay, so let's go ahead now and integrate with respect to y. Okay, so my outside limit is from 0 to pi over 4. Okay, so when you integrate this with respect to y, this is going to be I'll just put 1 over 2 outside here. Okay, because this is going to be like e to the 2y divided by 2. Okay, let me leave it like that. Then from 0 to natural log of the sec z like that, and you just have dz like that there. Okay, so now what does this turn out to be? So let's go ahead and do the evaluation. So this is from 0 to pi over 4. So if you plug in here, let me just do this. That 2 on the denominator, I don't know why I'm uncomfortable seeing it there. Let me put it outside. That would be 1 over 2, even better. Okay, so if you plug in natural log of z, so this would be like e to the power 2, where there's y, plug in natural log of sec uh, sec z like that. Then that's the upper limit. The lower limit, you plug in 0 where there's y. That's going to be e to the 0, meaning it's a 1. I believe it's something that we know by now. Okay, so now let's go ahead and do some simplification. Okay, let's go ahead and simplify some things. mm, okay, so have I left anything out? Okay, so for this one here, here's how you can simplify it. You have e to the power 2 natural log of sec z like that. So one thing that you have to keep in mind is that if I, for example, let me say I have a natural log of b, this can be written as uh, this can be written as natural log of uh, b to the power a. Okay, so what this tells me, okay, what this tells me is that I can write this as e to the power natural log of sec z squared. Okay, so the way again you can simplify this further is that everything here just goes down to be what? To be sec squared of z. Is because this is e here, and like you have e, it's more like you have e to the log base e of this. So you have e here and you have e there. Yeah, most call it cancelling out, so you just end up getting what you have there as more like the power without the natural log. Okay, so that's the simplification that we have gotten. Okay, so we have found out to say this is like 1 over 2. Okay, from 0 to pi over 4. We now have like sec squared z minus 1 dz. Okay, let's go ahead and do the final part. So this is 1 over 2. When you integrate sec squared z, you're going to get tan z. Remember, the derivative of tan is equals to sec squared, so this will be minus z there. Okay, evaluating from 0 to pi over 4. Once again, no need of taking 0 into consideration because tan 0 is actually 0. Why am I talking about it being 0? Where am I even getting this from? It's very simple. So tan z or tan z is equals to sine z divided by cos z. So sine 0, if you plug in 0 here, sine 0 is 0, so it's like 0 divided by cos 0 is a 1, so that's why we are saying tan 0 is a 0. That's where it comes from. Okay, so let's just go ahead and plug in the upper limit. So this will be 1 over 2. So tan pi over 4 is actually 1. This is tan 45. I'm just getting this from special angles. I'm not using any calculator. I'm not saying you cannot use any calculator, but you can. But I'm just looking at it from these special angles that we have known for quite some time now. So if this is 45, okay, pardon me, those lines are not straight. So this is 45. So that would be 1, 1, and that would be the square root of 2. So tan is equals to opposite over adjacent, and that's like 1 over 1. That's a 1. Okay, so you have 1 here minus z, just put pi over 4, and this turns out to be a solution. You can choose to write this as 1 over 2 minus pi over 8, 8 like that. Well, I choose to write the first one, okay, which is 1 over 2, then 1 minus pi over 4, and this is the solution to that interesting question that we had. And that's all in this video. Thank you very much for watching, and we'll catch you in another interesting video.